Okay, if you didn't get your exam on Monday, I forgot them in my office, so you can stop by and get it at your leisure, including yours, because you left yours behind yesterday. So, if there's any questions about scores or any of the older, if I misscored any of the other stuff from the rest of the semester, this week would be a good week to let me know, or before the final would be best. Okay, so to finish up with the anti-Markovnikov HBr free radical mechanism from last time, we basically, if we start with something like this, methyl cyclohexane, and we add HBr with peroxide, we're now going to do anti-Markovnikov addition of HBr. So let's see it. We have one more reaction after this that we can add to our chart. So this one should go on the chart as well as the mercuration. So what are we going to add to the double bond? We're going to add an HBr. How am I going to add it? Anti-Markovnikov. And so if I was doing this problem, I would basically say, okay, I have my methyl group, and so now I'm going to add my H and my Br anti-Markovnikov so that the hydrogen is added to the carbon with the least hydrogens in the double bond, and the bromine gets added to the carbon with the most hydrogens. So again, opposite of Markovnikov. Now, we said last time that this basically goes through a free radical mechanism. So the key species in this is the idea that the Br dot adds to the carbon in the double bond that makes the most stable radical intermediate. So the way we write the arrows, again, these are half arrows. They're sometimes called, I don't know if this book calls them fish hooks, because they look like fish hooks, although if you shade one in, it's basically a half of an arrow, and so it indicates one electron movement. We've been writing full-headed arrows, which means 2 electrons are moving. So in this case, if I think about splitting the double bond up and giving each carbon an unpaired electron, the bottom carbon is going to pair up its unpaired electron with the Br dot to form the carbon-bromine bond. And so that's going to leave then on the top carbon a free radical. And so in this case, we would get a tertiary free radical, which is more stable than the secondary free radical that I would get if I did Markovnikov addition, if I added the Br to the top carbon. So because the mechanism's changed and because the intermediate's changed, that's why it's now anti-Markovnikov versus Markovnikov. Okay. But the question about stereochemistry still exists. So this is not a bromonium ion. This is a Br atom that adds. So if we say that the Br added to the top, so I put a bold wedge in there, the question is, when the hydrogen is added by the free radical, will it be added to the top, the bottom, or will it be added 50-50? And so what we have to think of here is we have to think of what's the structure of a free radical. And the difference between a carbocation and a free radical isn't that much. Both of these are, this is an sp2 hybridized carbon because it just has 3 atoms that are attached to it. So that means it has 3 hybrid orbitals, which means that it's sp2. And then it has the unhybridized p orbital that's parallel to that trigonal planar geometry. When you have a carbocation, the p orbital is empty. So the nucleophile then could add 50% from the top, and it adds 50% from the bottom, because there's no preference over the 2 lobes. When you have a radical, the only difference is you now have 1 electron in that p orbital. And so that 1 electron is spending 50% of its time in each of the 2 orbitals. So when it adds the HBr, it's going to add that 50% of the time from the top, or 1 lobe, and then 50% of the time from the bottom lobe. So what's going to happen then is that in my final product, I'm going to have use the squiggly line that the book uses to indicate that it's a mixture of, it's a 50-50 mixture of bold and dashed wedges. If you see in the book, they will do this. That squiggly line basically means that you have 50% of the time you have a bold wedge, and 50% of the time you've got a dashed wedge. So it's just a way to indicate without having to write basically both of the chiral centers. And oftentimes the squiggly line might mean we don't know. We don't know if it's bold or dashed. Okay. So because the radical intermediate is sp2 hybridized, it's going to behave exactly like a carbocation. So HBr, you're adding anti-Markovnikov, and you will be adding 50% cis and 50% trans. There's going to be no stereoselectivity for this free radical halogenation reaction. So that's how we would write that product. Is there's going to be no it can never be stereoselective. So if you went back and you looked at my flowchart that I created, it's the first thing it asks is, does this reaction have a carbocation or a C dot intermediate? The C dot intermediate is the radical. So if it has either a carbocation or a radical intermediate, it is not going to be stereoselective. Could this be regioselective? Absolutely. And in this case, this reaction is regioselective only. Because adding the HBr Markovnikov and anti-Markovnikov gives me 2 different products. The reaction is anti-Markovnikov, and so therefore the major product has selected one over the other. So that kind of completes that mechanism. Right. And again, the most important thing is that because I changed the intermediate, and because now the bromine is the thing that adds first, it's going to add to make the most stable radical, whereas before the hydrogen added to give me the most stable carbocation. So that's how we flip the regioselectivity on this. And overall in the free radical mechanism, we'll talk more about this next semester because that's where it's placed in the textbook. But one of the issues with free radicals is that when a free radical reacts, it generates another unpaired electron species. And so the reaction continues. And that's a problem for free radical reactions because it means they never stop. So if you breathe, which you really don't have a choice in, part of the oxygen, a portion of the oxygen that you breathe in is in a diradical form. This is a paramagnetic form of oxygen. And so when you breathe in oxygen, you do have oxygen in your system that is basically a free radical form. And so what it wants to do is it wants to grab hydrogens from different things. Maybe not so much DNA, but whatever it comes into contact with. If it can take a hydrogen from that species, whatever that species is, then you'll end up forming the oxygen-hydrogen bond, but then that species, whatever it is, will have an unpaired electron, and then it's going to feel the need to grab a hydrogen from something else. So this kind of cascades down the line. And this isn't just true for biochemistry, it's also true for food. Because why we try and exclude oxygen from most food is because oxygen will react with the food and it'll cause it to spoil. So in food, what we do is we can add a molecule that has a basic structure of having an OH attached to a benzene ring. And there's a bunch of these. You can put a tertiary-butyl group there, or you can put maybe a couple methyl groups there. Those are the common structures of food preservatives. And what happens there is that when the oxygen in the air comes in contact and removes that hydrogen, what you end up making is a compound where now I can draw resonance structures for that by splitting up the double bond and maybe splitting this double bond up. I'll just write the first resonance structure, and we'll talk more about this next semester. But if I split this double bond and then paired up that electron, I would form a double bond there, and then I would have an unpaired electron on that carbon. And then I could do the same thing with the remaining two double bonds. So this becomes a very stable species because there's lots of resonance structures I can draw for that radical. And so it doesn't kill the radical per se. What it does is these molecules that would be called antioxidants, and there's many of them, what happens is they form a stable radical that then doesn't feel the need to go out and grab hydrogens from other molecules. So in our bodies and in food, we have these antioxidants that when the hydrogen is removed from them, they're perfectly stable and they don't continue the process. They kind of just stop it there. So they sacrifice themselves for something else. And we'll talk more about these, but this is the basics of why we need things like antioxidants. And if you look at all of them, these are phenol, because when you have an OH attached to the benzene ring, I think we've talked about this, that's called a phenol. These are phenol-based antioxidants. There's also, if you go back and look at the structure of beta-carotene from lab, how you had those double bonds that alternated in that whole structure. If you remove one hydrogen, you can draw a whole bunch of resonance structures. And so, like the beta carotene is a great antioxidant. You hear about vitamin E being an antioxidant. They all have the same properties, that once you remove a hydrogen from them, they form a stable radical because it's stabilized by resonance. And so this helps stop the chain process. So that's the basics of how to stop the free radical reaction, is to give something. So we don't have a choice. We need to breathe. You know, the alternative to not having oxygen in our system is that's not good. And so we need to have these antioxidant systems to keep those free radical mechanisms under control. All right, so that's anti-Markovnikov addition of HBr and our first encounter with free radicals. Everybody okay with that? Okay. The next reaction of adding things to double bonds, and we only have, this is it. This is the last one. This reaction is called Cis-Hydroxylation. So Cis-Hydroxylation does exactly what it says. I'm going to add 2 OH groups, cis. So what am I going to add? I'm going to add 2 OH groups. There's no Markovnikov, anti-Markovnikov, because it's now a symmetrical reagent. And I'm going to add 100% cis. Okay. So that's what we need to remember about this reaction. And then the question is, well, what reagents do we use? The reagents that we're going to use are basically inorganic reagents. They have metals in them. And so I'm going to show you the mechanism, kind of, but I'm going to show you enough of the mechanism so that if you had to, you could remember, oh, that's why it's cis. So let's take a review of shapes. Shapes of intermediates. Triangular intermediate means 100% trans. Square, cis. So the next one then is a 5-membered ring. So we can get to a pentagon. So here's what happens with these 2 reagents that we could use. I'll do the first one, which is going to be, we're going to add potassium permanganate to this double bond. So potassium permanganate, you've used that in general chemistry. It's purple. It makes a purple solution. It is an oxidizer because it will actually, in this case, add oxygens to our double bond. And so that means that molecule is being oxidized because it's gaining oxygen. And so that's what potassium permanganate does, is it oxidizes stuff. If you have a fish tank and it's basically, you have a lot of crud in there and it's really cloudy, you can add a couple drops of potassium permanganate and it will oxidize all that stuff, meaning that it'll add OH groups to it or add oxygen to it, make it water soluble so that the tank mysteriously becomes clear because you've taken all the insoluble stuff and made it soluble. Not too much to kill the fish, but enough to just oxidize all of like the fish waste or whatever's in there. So what we're going to end up doing is we're going to end up adding 2 OHs to the double bond. And those 2 OHs will be 100% cis. So why? Well, in order for us to understand why, we have to kind of write out the structure of the permanganate. And so potassium, remembers, +1. The permanganate ion is -1. So if I look at this, I've got an Mn multiply bonded to some oxygens, something like that, in terms of my permanganate ion. Right. So magnesium is a transition metal, so it doesn't really have to obey the octet rules. It can form an expanded octet. So here's what happens. What happens is I can think about moving the electrons this way. I can move this pair of electrons to the carbon and then move this pair of electrons out to form the carbon-oxygen bond, and then give this pair of electrons to the magnesium, or sorry, the manganese. Now, in our general chemistry, we know that things that oxidize themselves undergo reduction, right? That's what an oxidizer does. It oxidizes the other thing, but it itself undergoes reduction. And my favorite of the reductions is the LEO. Leo the lion goes grr. Leo, lose electrons oxidation, gain electrons reduction. So what's happening to this manganese is it's gaining a pair of electrons. So it is truly being reduced, which makes it an oxidizing reagent. So in this case, we can actually keep track of the oxidation reduction by noticing that the manganese is getting a pair of electrons. So it's GER, it's gain electrons reduction. So the species that I'm going to make is a 5-membered ring. So when the manganese adds its 2 oxygens to the double bond, it forms a 5-membered ring. A 5-membered ring is not big enough to stretch across the double bond. In other words, a 5-membered ring, because it's adding both oxygens at the same time, must add them cis. Because there's no way to add 1 oxygen and then take that 5-membered ring and stretch it around and have it add underneath. So because this is a 5-membered ring, transition state intermediate, whatever you want to call it, and it's, in this case, it's not quite clear. It's probably an intermediate, but we don't care about that because it just goes to the final product. But this 5-membered ring means that the 2 O's have to be added cis. They have to be added at the same time, and the ring isn't big enough to stretch across the double bond. So this is what sets up the cis stereochemistry of the products. And then what happens is the sort of inorganic part of the mechanism happens where the manganese gets removed so that we end up with our 2 OHs now having added cis across the double bond. So this is one of the reagents we can use to do the cis-hydroxylation, to add 2 OHs cis across the double bond as KMNO4. Does that, and again, I wouldn't ask you for this mechanism, but hopefully if you can remember, oh yeah, that's right, it's a 5-membered transition state. I'm adding the 2 O's at the same time, it's got to be cis. That's why I show you these, is so hopefully if you get stuck, you could go back and remember that. Or you can remember it to begin with so that you don't have to just say, oh, it's cis. It's cis because it has a 5-membered ring. Now, the problem here, it's a small problem because potassium permanganate's dirt cheap. But you have to use it in a 1-to-1 mole ratio. In other words, it takes a mole of KMNO4 per alkene. There is another reagent that reacts exactly the same. And that is, if I take my double bond and I react it with osmium tetroxide, which is OSO4. So osmium tetroxide will pretty much do the same thing. Only in this case, I'm going to take this pair of electrons, and then I'm going to move that there, and again, bring the pair of electrons back down to the osmium. So in this case, same 5-membered intermediate. Same thing, osmium's gaining electrons, so it's being reduced, which is the characteristic of an oxidizer. But the problem is that here is I need to get rid of this osmium part. And so what I actually do is I react it with H2O2, hydrogen peroxide. And so what happens when the hydrogen peroxide reacts with this species is that you end up forming your final product with the two OHs, again adding cis. But then what the hydrogen peroxide does is it reoxidizes the OSO4 back to its original form. So osmium is a metal that's exceptionally expensive. And so we can't react 1 molar equivalent of osmium with the double bond. That would be way too expensive. And so what happens is that we use a little bit of osmium sort of as a catalyst, and then we use the hydrogen peroxide to keep reoxidizing it so it keeps reacting with the double bond. So a little bit of osmium in this reaction will go a long way, because the hydrogen peroxide, which is also dirt cheap, will then keep reoxidizing it after it reacts. Okay. So that's basically cis-hydroxylation. So if I was to do this reaction with So if I said, what's the major product of this reaction? We could again go through our steps, which is, what am I adding to each of the carbons in the double bond? I'm adding 2 OHs. Markovnikov or anti-Markovnikov doesn't matter, because there is no Markovnikov or anti-Markovnikov, because this is a symmetrical reagent. Since it's a symmetrical reagent, the reaction is not regioselective. You got to be aggressive with your answers, even though it's the last week, right? Did I tell you my Dr. Weaver story about the last week of classes? No, I did think I was in the 1 o'clock class. So when I first got here a long time ago, Dr. Weaver taught organic with me and knew more he forgot more chemistry than I'll ever know. But he's like, oh, well, the last couple of weeks they just won't listen to you. And I'm like, weeks? Last 2 weeks? And he's like, yeah, it's just everybody's burned out. And then, but I came from OU where it was like maybe week 2, 1 sometimes when people turned off. So I guess it was an improvement. But remember, you can completely disconnect after your last final, right? Doing that beforehand could have very bad consequences. So as tough as it is right now for everybody, you just have to kind of keep moving until next Friday when it will all be over for this semester, and then it starts all over again. Oh, and by the way, next semester in organic, we have to remember all the stuff that we learned this semester. So you got to somehow keep it in there and not let it escape. So I get it. It's a long week. So 2 OHs. How do we add them? Cis. So they both get bold, or they both get dashed wedges, and then the CH3 gets the opposite wedge. So this would be the case whether it was osmium tetroxide or KMNO4. Actually, you know what I forgot on the KMNO4? I forgot that it's KMNO4 and base. So I should go back here. It's KMNO4 and OH minus. So it's the hydroxide that strips the manganese off over here. So on Friday, we're going to have another KMNO4 reaction with a double bond. Only this is going to be KMNO4 and acid. KMNO4 and acid does something completely different than KMNO4 and base. So the only mnemonic I can give you for this is that KMNO4 and OH minus adds 2 OH minuses. So KMNO4 and base is going to add the 2 OHs. The KMNO4 and the acid is a much harsher set of reagents, and it's actually going to cleave and break the double bond. But we'll get to that on Friday. All right, so this reaction is what? Is it regioselective? No. Is it stereoselective? So regioselective, no, because it's a symmetrical reagent. Stereo, yes. Don't know. So, in terms of, we can boil regioselectivity down to basically 2 things, which is essentially what the flowchart does. Did I add the 2 groups 100% cis or trans? Yes. Did I form a product with 2 chiral centers? Yes. I formed a product with 2 chiral centers. If those 2 statements are true, you can forget about the flowchart, because the reaction will be stereoselective. So I'm adding 2 OHs cis, 100% cis, and I did form 2 chiral centers. Therefore, this reaction is stereoselective. Okay. So, that's cis-hydroxylation, forming 2 OHs. Everybody kind of okay with that? All right. Then the last group of reactions, or first reaction, then some follow-up ones, is forming what we call epoxides. Epoxide is kind of a common name for this group. They're technically called oxiranes in the IUPAC system. Here's what an epoxide is. An epoxide is a 3-membered ring that has an oxygen in it. So the oxygen is part of the 3-membered ring. And these turn out to be important intermediates. So the first question is, how do we make epoxides? And then what can I do with them? So there's two ways to make epoxides. The first way is to make a bromohydrin. Right, so here's our bromohydrin from, I don't know, 1 to 2 to 3 weeks ago. So what we do is if we treat the bromohydrin with something like hydroxide, the hydroxide can deprotonate the OH of the bromohydrin. And remember that when we made bromohydrins, the bromine and the OH group were always trans. So that once I deprotonate that OH and make it O-, it can now act as a nucleophile and attack the carbon next to it from the top or the bottom, in other words, opposite the bromine, so that it can kick off the bromine. This is an SN2 mechanism, and then we can form our carbon-oxygen bond and form our epoxide. So when we made bromohydrins, it wasn't quite clear, like, okay, what's the use of those? The use of those is that you can use them to make epoxides. Okay, so that's one way to make epoxides. Another way to make epoxides is to just simply take the double bond and react it with a single reagent. The single reagent is called a peroxy acid. So that per term means that something has an extra oxygen in it. Right? Hydrogen peroxide means hydrogen oxide would be water, but hydrogen peroxide means I've got an extra oxygen in it, which makes it HOOH. So if I have a carboxylic acid and I turn it into a peroxy acid, I just add an additional oxygen in there. And so what happens is that that extra oxygen is going to plop itself right on top of the double bond and make the epoxide. So this is a one-step mechanism. We're not going to talk about explicitly the mechanism, but the key thing is the oxygen just adds to one side of the double bond, and both bonds are formed immediately. So it's a concerted mechanism. It's one step. So that when you make the epoxide, the stereochemistry of the double bond is preserved. So let's say we've got two R groups that are cis and two H groups that are cis in this double bond. When the oxygen plops itself on the double bond, there's no rotating. So that over here, the two R groups remain cis and the two H groups remain cis as well. So the stereochemistry here is preserved in the epoxide. And so in this reaction, this now, you could say, is that stereoselective? Is it regioselective? It's neither one of those. We can now use our new term, which is called stereospecific, which the book introduced a couple of weeks ago. So this reaction is one that is stereospecific. So what does stereospecific mean? Well, here's what it doesn't mean. stereoselective and regioselective, our focus was on the products, right? Did we make more than one product? What was the relationship with those products? Did I choose one of those products? With specificity, the focus is on the reactant. So this reaction is stereospecific because if I change the stereochemistry of the reactant, I get a different stereochemistry of the product. So in other words, when it's cis, the product is cis, but if I change this reactant to trans, the product is going to be trans. So the specificity means that if you change the stereochemistry of the reactant, you'll get a different product. And so this is our example of a stereospecific reaction. Now, it doesn't always mean that the stereochemistry is preserved, because we actually know another stereospecific reaction, SN2. If I take an R chiral center and I do an SN2 reaction on it, what's my product? It's inversion, so if I start with R, I end with S. If I change that R to S, what happens to the product? It now becomes R. So I change the stereochemistry of the reactant, what happens to the product? It becomes different. Okay? So that's stereospecificity. And so this is an example of it, as is SN2. There are other stereospecific reactions, but we're going to hold off on those until next semester. All right, so we can make an epoxide simply by adding a peroxy acid or making the bromohydrin and then reacting it with base. But what do we do with epoxides? Okay, here is my epoxide. The first thing I'm going to do to this epoxide is, there's two sets of conditions that I can use. One is called acid catalyzed, even though it's not. It's not catalyzed. I can add acid to this, or I can directly add a strong nucleophile to this. Now, let's add the acid to it. Okay, so here's my H+. What's going to happen? I'm going to I'm going to protonate the oxygen. Right? That's going to be our standard answer from now on whenever we have, well, it's from a while ago on. Whenever you have an oxygen or a nitrogen species and you're reacting them with acid, the first step is protonate the oxygen or nitrogen. Okay? It's the first step. Great. Protonated. I'm having a sense of deja vu. That means we've seen this before in French. Anybody else having that sense? Anybody else feel like they should be having that sense? From Monday and from the last couple weeks? What do I have here? What shape do I have? I got a triangle. I had a triangle with one of the atoms with a plus charge. Is that helping anybody get their... What's it look like? Two possibilities. Triangle with a plus charge at the top. Could be this or it could be that. It looks like the intermediate of the mercuration that we talked about a long time ago, which was Monday. And what did the mercurium ion look like that we had seen earlier? Starts with B. Looks like a bromonium ion. So this looks like a bromonium ion or a mercurium ion. And in those cases, what did they do with when the oxygen doesn't really like the hydrogen or doesn't like the positive charge? What does it do? It pushes it away. Where does it push it to? Pushes it to those two carbons. Because once I protonate the epoxide, I can open it up. Meaning that, let's see, how about I'll add a water. So the reaction would be H plus H2O, and so the first step is protonate the oxygen, and now I have a water molecule. So the water molecule is going to react with that protonated epoxide. How's it going to react? Markovnikov and anti-Markovnikov aren't really relevant here. We can't really use those terms. I definitely know that the water is going to add from which side of the epoxide. From the opposite side of where so it's going to react underneath, right? So this is definitely going to react underneath so that this water, which will eventually become an OH, and this OH will become trans. Now, which carbon is the water going to add to? Carbon A or carbon B? Or if you don't know specifically A or B, which one is the water going to add to? The carbon with most substituted, because that's the carbon with the most positive charge, which in this case is going to be A. So the water is going to add to carbon A, and then that bond is going to break, and the OH is going to swing to the right. And so I'm going to end up with the final product here being having the oxonium ion, over here having the OH, and then I'm going to lose the H plus off the oxonium ion. So if I add H plus H2O to an epoxide, the net result is that I added 2 OHs trans. And where did this epoxide come from? It came from a double bond. So if I go through this epoxide intermediate, I can now add my 2 OHs trans to each other, which is kind of important because I just showed you how we could add 2 OHs cis. So now I have a choice. I can add 2 OHs cis or I can add 2 OHs trans. But now I can think about all the other nucleophiles I could add to a protonated epoxide. Maybe I add HBr to it. Maybe I add H plus in an alcohol. And now I have the ability to add that H, or have that OH in whatever other group trans. So we'll finish this up, and then we have to talk about ozonolysis on Friday, and then any questions you have. Did everybody get an email about the course evaluations? So you can fill those out at your leisure. I will provide incentive for that on Friday, along with my historical rant on other websites where you get to provide your feedback on faculty. This is your official opportunity to provide feedback on the class. RateMyProfessor.com is not official, so I will go on my rant on them on Friday. It is very humorous, and I'll talk about the incentive for filling out the course evaluation, other than if there's something you really like, you need to tell me so that I can do it next semester. If there's something that needs to be changed, tell me that so I can think about doing that next semester. All right, so that's what we'll do on Friday. Oh, and the